In the last section, we discussed the naming and the preparation of alkyl halides. In this section, we're going to look at the reactions of alkyl halides. Alkyl halides can undergo many types of reactions. In this section, we only look at some of it. This includes the formation of Grignard reagents, Gilman reagents, and the coupling reactions. Alkyl halide can be used to make organomagnesium halide, and this is called a Grignard reagent. Alkyl halide can also be used to make organolithium reagent. Combining organolithium reagent with copper iodide will form lithium diorganocopper compound, which is called a Gilman reagent. Now, one of the very useful reactions for Gilman reagent is the coupling reaction we are going to see. And we are also going to discuss the concept of organic oxidation and reduction reactions. When magnesium metal is added to an alkyl halide, this R represents alkyl group. The simplest case is methyl group. And X represents a halogen atom, can be chlorine, bromine, or iodine. The magnesium atom will insert between this carbon-chlorine bond, forming an organometallic compound. In this case, is the magnesium methyl chloride, and this is called a Grignard reagent. Ether and THF are used as a solvent for the reaction. So for this type of reaction, the bromine, alkyl bromide, alkyl iodide is most reactive. Alkyl chloride is less reactive. Fluoride rarely react. Now, there's an important feature for this reaction. For alkyl halide, because chlorine is very electronegative, and so it pulls electron away from carbon, so the carbon is positive charged, chlorine is negative charged. Okay, so this is a common feature for alkyl halides, in which carbon is partially positive. By adding magnesium forming Grignard reagent, because magnesium is a metal that has low ionization energy, it will lose 2 electrons, form a magnesium 2+. Where does the electron go? The electron go to chlorine and the methyl group. So not only the chlorine is negative charge, the carbon also becomes negative charge. And this is a very important change. The polarity changes from positive carbon to negative carbon. And this has a very important consequence for the reactivity, and we're going to see in the future. So here is a setup for synthesis of Grignard reagent. A round bottle flask containing the alkyl halides with magnesium metal, and the reaction is heated, reaction mixture is heated, and you have a condenser so that the solvent will condense back for the reaction. And on the top, there's a drying reagent to remove water. And we'll see why this reaction is sensitive to the presence of water. Here is another example of Grignard reagent formation. A iodomethane, when magnesium metal is added in solvent ether, magnesium will insert between carbon iodine to form methyl magnesium iodide. Note the polarity change. Here, carbon is positive, and in the Grignard reagent, the carbon is negative charged. So quantum mechanical calculations show the methyl and iodo both are red color, means they are negative charged. Now, negative charged carbon is called carbanion. Carbanions are very reactive. In the future, we'll see the reaction that whenever you have a Grignard reagent, all right, the negative charged carbon will attack positive charged carbon. For example, a carbonyl carbon, that's a positive carbon, and that give you alcohols. In the last slide, we show that in Grignard reagent, the alkyl group has a negative charged carbon called carbanion. For example, if this is a methyl group, so methyl magnesium bromide. Now the carbon of methyl group has a negative charge. We also know that water has a polarized bond. Oxygen has a negative charge. Hydrogen has partially positive charge. So if the system contains a Grignard reagent with water, this negative charged carbon, which is carbanion, will combine with a positive charged hydrogen, forms a methane. Okay? And therefore, if the goal is to synthesize Grignard reagent, then the system cannot have water. It's sensitive to water because water will destroy the Grignard reagent. On the other hand, the reaction of Grignard reaction with water can also be used for synthesis. For example, if we want to convert 1-bromohexane into hexane, we need to replace bromine by hydrogen. So one way you may think is just add water. So will the hydrogen replace bromine? The answer is no, because the carbon is positive and the hydrogen is also positive. They don't react with each other. Okay, they both are positive charged. Now, one way to do it is first you add magnesium in ether condition solvent. The 1-bromohexane becomes Grignard reagent, which is 1-hexyl magnesium bromide. So now the polarity of the carbon change to negative. So now this becomes a negative carbanion. So now if you add water, then this carbon will react with the proton of the hydrogen and forms hexane. We just showed what is a Grignard reagent and how to synthesize it. So now let's look at some similar organometallic compound, and one is alkyl lithium reagent. When lithium is added to a alkyl halide, for example 1-bromobutane, butyl lithium is made. Note the difference. If we add magnesium, the magnesium atom will insert between the carbon-bromine bond, so forming butyl, okay, magnesium bromide. And this is a Grignard reagent. Magnesium is 2+, bromine is negative, carbon is negative, and so the charge is balanced. Now in butyl lithium, because lithium can only lose 1 electron, so lithium is 1+, and therefore it only needs 1 negative carbanion. No bromine is needed. So Grignard reagent has a bromide, and butyl lithium doesn't. Butyl lithium only have lithium and a carbanion. And butyl lithium, since butyl lithium also has a carbanion, so the reactivity of butyl lithium resembles that of Grignard reagent. Okay, we're going to see in the future. Now there is one reaction we are going to see for alkyl lithium, and here is that it reacts with copper iodide to form the dimethyl copper lithium. So a copper connected to methyl. Okay, copper is 1+, methyl is negative. So the whole ion is negative, and therefore you need a positive lithium combined together. That's called lithium dimethyl copper reagent, which is called Gilman reagent. Gilman reagent also contains carbanion, so it has 2 carbanion. So the reactivity also similar to Grignard reagent and alkyl lithium reagent. But there's some differences, and one is will perform coupling reaction, and we're going to see in the next few slides. Here is a comparison of these organometallic compounds. In Grignard reagent, a magnesium connects to a bromine and a carbanion. Magnesium is 2+, bromide is negative, and carbanion is negative. In alkyl carbanion connects to lithium. Lithium ion is +1+, carbanion is negative charge. In Gilman reagent, there's a copper connect to two alkyl group. Okay, both are carbanion. Copper is 1+, and there's a lithium ion balance the charge. One of the very useful reactions Gilman reagents can undergo is a coupling reaction. So suppose we mix a Gilman reagent with an alkyl halide. In alkyl halide, the carbon connected to the halogen atom is positive charge, and the carbanion connected to copper is negative charge. So the negative charged carbon, positive charged carbon forms a new carbon-carbon bond. So the net effect is the halogen atom in the alkyl halide is replaced by one of the alkyl group from the Gilman reagent. Here, 10 carbon of the alkyl halide now becomes 11 carbon alkane. The actual carbon comes from one of the alkyl group from the Gilman reagent. Suppose we want to add 2 carbon. Instead of CH3, we want to add CH2CH3, so 2 carbon. Then we need to change Gilman reagent to dimethyl or diethyl. Instead of dimethyl, it's diethyl copper lithium. Then one of the ethyl group will replace iodine and forms a longer chained alkane. Okay, that's the coupling reaction. Here shows more examples of coupling reactions. A Gilman reagent, in this case, is dibutyl copper lithium, react with vinic iodine. So the iodide will be replaced by one of the butyl group in the Gilman reagent, forms a new carbon-carbon bond. A Gilman reagent, in this case, is dimethyl copper lithium, react with iodobenzene, so iodide will be replaced by one of the methyl group, forms a toluene. In summary, one of the applications of alkyl halides is to make organometallic compounds. This includes Grignard reagent, organolithium reagent, Gilman reagents. If we mix alkyl halide with magnesium in ether solvent, a Grignard reagent is formed. Here's another example. Alkyl bromide, magnesium forms a Grignard reagent. Now, Grignard reagent is very sensitive to water because the carbon connected to magnesium is a carbanion, negative charge, and water hydrogen is a positive charge, and therefore the reaction will form alkane. Okay, the magnesium bromide is replaced by the hydrogen. When alkyl halide is combined with lithium metal, a organolithium reagent is formed. When organolithium reacts with copper iodide, dimethyl copper lithium is formed, and this is called Gilman reagent. Gilman reagent can undergo coupling reaction. So if you add a Gilman reagent, in this case dimethyl copper lithium with alkyl halide, then the negative charged carbanion, positive charged carbon will connect to form a new bond. So the iodine is replaced by one of the methyl group, form a longer chained alkane. Practice. How would you carry out the following synthesis? to make butyl cyclohexane from cyclohexene, cyclohexanol, cyclohexane. If we compare reactants and product, we see that there's an alkyl group is added to the ring, and therefore the reaction must involve a coupling reaction. And in this chapter, we learned that coupling reaction is between a Gilman reagent and a alkyl halide. So one possible is this butyl group comes from a Gilman reagent, and that is CH3, CH2, CH2, CH2. It's a butyl, so dibutyl copper lithium. So that's a Gilman reagent, and the other part comes from a alkyl halide. So it must be cyclohexyl chloride or bromide. Okay, so both works. So if we combine this together, all right, that will give you coupling reaction. So for example, the chloride will be replaced by one of the butyl group, give you the final product. So the question now is, how do you make this chloro or bromo cyclohexane from cyclohexene, cyclohexanol, cyclohexane? So in this chapter, the first part, we learned how to make alkyl halides. Okay, so one way to make alkyl halides is from the double bond by electrophilic addition. So in this case, if we want to chlorocyclohexane, we can add HCl. All right. If we want to make bromide, we add hydrogen bromide. So that's an electrophilic addition. Now, how do you make chloro or bromo cyclohexane from cyclohexanol? Okay, we learned in this chapter we can make this alkyl halide from alcohol by substitution reaction. Okay, and if it's tertiary, we add HCl. If it's secondary or primary, we need to use a thionyl chloride or phosphorus tribromide. Okay, so that's how you make alkyl halide from alcohol. Now, to make alkyl halide from alkane, we learned in this chapter that we have to use a radical reaction, a radical halogenation reaction. So you need UV light, you add chlorine. Okay, that will give you the alkyl halides. All right, so here is the answer. So the coupling reaction, all right, you can add a Gilman reagent with alkyl halides, which in this case we use bromide. Okay, so to make this bromide, all right, from double bond, that's electrophilic addition, we add hydrogen bromide. From alcohol, we add the phosphorus tribromide because it's a secondary. All right, if it's tertiary, you can simply add HCl or HBr. Okay, if it's alkane, then radical chain reaction. So you add bromine under light. So after you make this bromo cyclohexane, then it undergoes a coupling reaction that will give you the final product. Please work on problems 10.9, 10, 11, B, and C. The answer keys to these questions are on the back of the textbook. Additionally, question 10.26 is also a good question for you to practice. If you have a question, please ask.